In this video, we're going to look at Unit 3, Lesson 13, which is using the Pythagorean Theorem and Similarity. So you can find this on page 92 or right around there in case the book numbers have changed. So what we're doing in this one is just looking to see, is triangle ADC similar to triangle CDB? So let me get some color in here to highlight which triangles we're looking at. So here's triangle ADC. And then triangle CDB is this one. So CDB would be this triangle over here. So we're trying to decide if these two triangles are similar. Remember, you've got 3 ways to prove that triangles are similar: showing that they have 2 sets of angles that are the same, showing that all 3 sets of sides divide to the same ratio or are proportional, or seeing that one angle is congruent in both triangles and the sides on either side of that angle are proportional to one another. So pause the video, see if you can figure out how these triangles are similar, then come back. All right, so I personally think proving by angle, if possible, is the easiest. And so that's the one that I'm going to look at, but just know that you could have done all 3 of them in this case. There's not just one way to have done this. So if we take a look at this triangle here, I'm just going to label the angles. So they gave me that this one here is 53. And they gave me this one is 90. Remember that the interior sum of a triangle is 180. So I could do 180 minus 90 minus 53, and that would give me this one of 37. So then if I take a look at this other triangle here, this blue triangle on the side that we were trying to prove is similar, I know that they told me that this one is 37. I also know that this one would be 90 since it makes a straight line with another 90-degree angle. So then I can see that 2 of the angles are equal, a 90-degree angle and a 37-degree angle. So automatically, those 2 triangles are similar by angle. If you were looking at the other ones, you would just be dividing out these sides. So here's the 3 sides of the blue, and then here's the 3 sides of the orange. And you would just divide out similar sides here. Okay, so 5.4 is the smallest and 7.2 is the smallest. So divide those. 7.2 is the middle and 9.6 is the middle. And then 9 is the longest and 12 is the longest. So if you divide each of those down, you would get 0.75 and show that the triangles are similar that way as well. And so if we're looking at this, so how many triangles did you actually see? So we highlighted 2 triangles, but then there's also this larger triangle. So there's actually 3 different triangles that we could possibly see here. And how many of them are similar? So we already know the 2 smaller ones are similar, but if we take a look at this larger one, you can also see that this one has the exact same angles as well. Since this is 53, this is 37, subtract those from 180 and we would get 90 here. So this has a 90-degree, a 37-degree, and a 53-degree angle, just like these 2 did. So this larger triangle is also similar to those smaller triangles. All right, then before we move on, I want to just discuss the Pythagorean Theorem or remind you of this and do a couple examples. So remember that the Pythagorean Theorem is used in right triangles. Okay, so you have to see a right angle. Across from the right angle is that hypotenuse, okay? And so Pythagorean theorem tells us that we square the hypotenuse. So we do c squared, and that will equal the legs squared and added together. So we generally call the legs A and B, so A squared plus B squared. It's really important here that you make sure that the hypotenuse is what you plug in by itself. C squared equals the legs squared and added together. So let's look at two examples. I like to just highlight where the hypotenuse is because it's the most important piece. So in this triangle across from the 90 is the hypotenuse. That's what we're looking for in this one. Okay, that's actually our C value. So the hypotenuse squared equals the legs squared and added together. So x squared in this case equals 6 squared plus 8 squared. Doesn't matter the order that you put the 6 and 8 in, you could flip those. So x squared equals 36 plus 64. So x squared is equal to 100. And so to find, to get rid of the squared, we would square root, and we get x equals 10. So the hypotenuse in this case is 10. Also remember that the hypotenuse needs to be the longest side. So make sure that your answer makes sense compared to the other measures you have. So 10 is bigger than 6 and 8, so that's great. This is working out. Then the second example, here's our 90-degree angle. Across from that is the 14, so that's our C value. Okay, that's our hypotenuse. So 14 squared is equal to the legs squared and added together. So our legs are 9, so 9 squared, and then the leg that we're looking for, so we can just call that x. So 9 squared plus x squared. And so then we do 14 squared, which is 196. And that equals 81 plus x squared. So now in this case, our x squared isn't by itself. So we first want to get rid of this 81 by subtracting 81 from both sides. And so then 196 minus 81 is 115. 81 minus 81 is 0, so we just have x squared. Now we have our x squared by itself, so we can square root both sides, and you can just do the decimal version of this. So square root of 115 in your calculator gives you that x equals 10.72. And then again, check that in comparison to the other measures in the diagram. And so 10.72 is a leg, that's less than 14, so that's good. So write this Pythagorean theorem down on your reference chart for Unit 3, Lesson 14. You can pause the video and get this written down and then come back once you're done. All right, then another vocab word that we're going to use today is altitude. And an altitude is just a segment in a triangle that connects a vertex, okay? So the vertex to the opposite side with a right angle. So from any vertex, a segment drawn perpendicular to the opposite side is called the altitude. So this vertex directly to the other side at a 90-degree angle would be the altitude. It's often also called the height of the triangle. Also, when you're flying a plane, you're flying at an altitude, okay? That's a height, okay? Or the perpendicular distance from the plane to the ground. All right, in activity 13.2, we're going to be using some tracing paper if you have it. Otherwise, I have tracing paper on my screen, so you can just do it along with me. You're going to do some tasks, and then we're going to discuss it. So to start this, the first thing I want to look at is using the vocab that we just talked about. So can you determine which segment is the hypotenuse in this diagram? And can you determine which one is the altitude? So think about that, pause the video, and then I'll tell you the answer. All right, so remember that the hypotenuse is directly across from the 90-degree angle. So in this case, we're looking at triangle EFH, so this larger triangle here. So the right angle is here at E, so directly across from that would be the hypotenuse. And then the altitude would be where we see a vertex connecting to the opposite side. And so in this diagram, this would be the altitude. And then can we figure out the length of this hypotenuse in the triangle? And so then we'll want to use our Pythagorean theorem that we just used. So we're looking for this value up here of this hypotenuse. And so we remember that it's the hypotenuse squared equals the legs squared and added together. So our legs in this triangle are 12 and 16. So 12 squared and 16 squared. So 12 squared is 144, 16 squared is 256. Add those together and we get 400. Square root that and we get that the length of that hypotenuse is 20. So this is 20, which again makes sense. It's bigger than both 12 and 16. So then let's take a look here. So here's where the tracing paper comes in. So if you have tracing paper, certainly pause the video, get your two different triangles traced so you can do it with me. But in this diagram, so if I move this over, what we're trying to do is prove that all of these triangles are similar to each other, or convince ourselves, right? And so if they're similar, they would have the same angles. So we already know, because this is the same measurements from our first triangle, that these two smaller pink and orange triangles are similar to each other. But if you need to convince yourself of that again, okay, you can just rotate this tracing paper. We know that they have the 90, and now we can see, if we look at this, that H is the same as E, and also that E is the same as F. So all of those angles are the same, meaning that those two triangles are similar. So then if we look at this pink triangle to the larger triangle, we can see that it has angles the same by looking here at G is the same as this larger E. And whoops, then also this angle is the same as the larger F. And then H, of course, is shared in both triangles and the same as itself. So certainly that pink triangle is also similar to the large triangle. And then we can do the same with this orange triangle, matching it up to the larger triangle's angles to show that the angles are the same. So we've got this one being the same. F is shared in both triangles, so it's certainly the same. And then we can show that E and H are the same size here. And so we see that these triangles, all three triangles, are certainly similar. So just convincing ourselves of that. So now that we've talked about that they're similar, so let's write some similarity statements. And I find it easier to kind of redraw these. So I'm going to redraw each of these. So I've got this smaller triangle, okay? And then I've got the kind of what I'm calling the medium-sized triangle. So if you need to, I would do this, pause the video and draw these two triangles so that you have kind of all of the triangles separated out here. I'm also going to highlight this larger triangle in blue. So here's kind of all three triangles that we are talking about. So let's write a similarity statement that compares these. So for this first triangle, I'm just going to call it triangle EFH. Okay, so I went here, angle E, which is the 90-degree angle, to F, which is the 37-degree angle, and that F is kind of hidden under there. And then to H, which is this 53-degree angle. So now what we want to do is in each of the other triangles, go in that same order. So for this orange triangle, okay, the 90-degree angle is G. So we went 90, 37, 53. So 90, 37 is F, and then the 53-degree angle is E. For the pink triangle, okay, again, 90, 37, 53. So 90 is G, 37 would be E, and then the 53 is H. So getting those written, matching up the corresponding parts. Number 3 then asks you to figure out the scale factor. So remember, scale factor, we need to have similar parts or corresponding parts to compare. So when we look here in the pink and the orange triangle, the segment that they give us is the hypotenuse. And so we would like to compare the hypotenuse in all of these diagrams. That will help us get the scale factor. So we want to compare similar parts here. And so when we do small to medium, okay, so we're going small triangle to medium triangle. Remember, you want to take the new measure first. So 16 divided by the original measure, and that is 12. So the scale factor here would be 16 over 12. And we could certainly simplify this because both of these divide by 4. So divide by 4 and you'd get a scale factor of 4/3. That would take the small to the medium. Then medium to big. So the length in the big triangle, because we want the second one first, is 20. So the hypotenuse in that one divided by the hypotenuse in the orange. So 20 to 16. And then simplifying that, both divide by 4. So that would be 5 to 4. And then finally, scale factor from small to big. So bringing the small one to the big one. So hypotenuse in the big compared to hypotenuse in the small would be 12 to 20. And then simplify this. So divide each by 4. Would be 5 to 3. So those are the scale factors that bring each triangle to the other. So if we wanted to go small to medium, that would be a 4/3 scale factor. Medium to large would be 5/4, and small to big would be 5/3. So now let's actually determine the lengths in each of these triangles. So we already figured out HF. Okay, so HF is the hypotenuse of the large one. So we already know that that's 20. So now we want to find GF in this orange triangle. So we want to find GF, and then we want to find GH. Okay, so those are the two parts that we want to find. And so we know here we've found scale factors. So if we just compare these parts here, and let me highlight what we're doing here. So in this triangle, this leg here compares to this one in this triangle, right? And we know that the scale factor to bring medium to big is 5/4. But we want to go, we have the big, so we want to go backwards, right? So we want to divide by that 5/4, okay, to go backwards, or just flip it, okay? So multiply by 4/5, and that would get us GF. So if we take the 16 times 4/5, that would get us the length of that one. So 16 times 4/5 gives us 12.8. So then looking at it again and now doing it for Y. So if we're looking at this one, So if we're looking to find, well, I called it y, right? GH. So if we're looking to find this one, okay, this one is similar to this leg because it connects the 53 and the 90. And we know that the scale factor that takes the small triangle to the big triangle is 5/3. So if we were going to go here, it would be 5/3. So the backwards version, okay, is just flipping this. So to find y, or HG, we would do 12 times 3/5 if we're going the opposite direction. And so 12 times 3/5 gives us 7.2 for the length of that segment. All right, so then that's not the only method you could have used. You could have done Pythagorean Theorem once you found another one. So we did do Pythagorean Theorem here. You can use scale factor like we did. You could also use equivalent ratios. So if the scale factor way that I was doing it was a little bit difficult, if you wanted to use equivalent ratios, you certainly could. And so that's like if we were finding this one, okay, this one compared to here, and then we know that these ones compare. So you could have set up a proportion that was y compares to 12, and then 12 compares to 20, and you could have set up that way and cross multiplied. And so you could have multiplied these two together and then divided by 20, and you would have gotten the same answer that we did. Or when you were trying to find FG here, okay, FG went with 16. So again, you could have done X compared to 16. And then you could have compared hypotenuse to hypotenuse again. And then cross multiplied and divided and gotten those same answers. All right. Then the final thing that we're going to talk about is continuing on with these tangled triangles. So take a look at a new diagram. Is there some mathematical questions you could think to ask here? And then just write down 2 of those questions and then come back to the video. So just think about what could we possibly ask in this next activity. So certainly there's a lot of questions to ask here, right? Like, are the 2 triangles similar? What's the length of BC? Could we figure out the length of AD or BD? Is there a way to find the angle measures? Okay, so all sorts of things you could have asked here. So using this diagram, just first off, convince yourself that all 3 of these triangles are similar to one another. It's kind of like what we've done, except for there's no angle measures listed here. So figure out how these 2 triangles are similar. Do you think they are? Then write as many equations about the proportional side lengths as you can. And then see if there's anything you notice about these equations. So pause the video, then come back for that. All right, so some different ways you could have convinced yourself that these are similar. You could have traced them like we did in the last one and just kind of rotated to C so that you found out that this angle measure here is the same as this angle measure here, and that this one is the same as this one, and then figured out that they have all 3 of the same angle measures that way. Maybe you said, all right, if this is a right triangle here, which it is, okay, because we've got this right angle here. If I called this X, then this angle would have to be 90 minus X. And this larger triangle here shares the X, right? So this big triangle shares the X here and has a 90. So then this angle here must also be 90 minus X, and said, all right, all of those are the same. You also could have just measured with a protractor and convinced yourself that way. But either way, we just want to make sure that we recognize that these are similar triangles. Then you could set up some different proportions. Okay, so kind of whatever you want here. I'm going to look at these two triangles first. And so if we set up some proportions here, we see that AC is the hypotenuse, okay, in this purple triangle. So if I compare AC, I would compare it to the hypotenuse in this green triangle, which is BC. So AC over BC. And then I could look at like this little leg here. So the shorter leg AD would then compare to the shorter leg in the green triangle, which is DC. Okay, so there's a proportion we maybe could have set up. Could have also looked at, in this purple triangle, the shorter leg, and maybe I'll just compare two in the purple triangle. So shorter leg to longer leg, and that equals, and then do the same thing in the green triangle, the shorter leg DC to the longer leg BD. Okay. I could also go to looking at the larger triangle. So comparing this little purple triangle, if I did, again, maybe the shorter leg in the purple triangle to its hypotenuse, then I could do that with the larger triangle as well. So the shorter leg in this big triangle is AC compared to its hypotenuse AB. And you could keep going with a lot of those different proportions. And so what did you notice about these equations? Okay, various things you could have noticed. But something I noticed in these two equations is that they use kind of the same length here, right? AC is in the diagonal in both, and DC is in the diagonal here. So lesson synthesis, finding the measure of all the missing angles in this, and how do you know? So if this large angle here is 90 and this one is 32, then this one, we would subtract those from 180, and that would give us 58 degrees here. We also know that this one is 90. You also can figure out these little angles, right? Because this is in this triangle, so subtracting 90 and 32 would give us 58 for this one. And then over here, okay, either you could subtract it from 90 since you know the red and green angle total 90, or you can subtract 58 and 90 from 180 and get 32 for this one. So then we know that all three of these triangles are similar because they share the exact same angles. And so then by angle, they would be identical. Tons of equivalent ratios you could set up here because you've got all sorts of congruent triangles here, or not congruent, similar triangles here. So if you kind of set up, like if I set up ratios with this shorter, or with this little blue triangle, so on the top, if I go short leg to medium leg to long leg, then I could look at this medium sized triangle over here and do the same thing. So then I could go short leg, medium leg, and then long leg being the hypotenuse. That's going to give me a bunch of ratios. I also could have done that with this larger triangle too, because the shorter leg here is CA, the medium sized leg is CB, and the long leg is AB. So I could have substituted these three measures in here as well and gotten some more ratios. Like if I just deleted these out, okay, I could have substituted these in, and this would give me a bunch of different ratios as well. So when we have a right triangle with an altitude drawn, we end up with three similar triangles, and that opens up a whole lot of possibilities for figuring out using Pythagorean theorem, using some different proportions, scale factor, all sorts of things. And so if you just want to highlight some of this stuff, this is the stuff I think is important in the lesson summary. Get that highlighted. Then you can try the cool down. And if you need help on that, make sure you reach out to your teacher.